let's pull up hyperelasticity. So this is a fun one. So the nonlinear plasticity and nonlinear elasticity, we can essentially use one tensile test curve. I'm going to show the use of hyperelasticity, which is, massive deformation that still goes back to shape, using a 2D simplification option. So if the model's loads are symmetric and the part is symmetric about an axis, or if it's relatively thin and we can cut a section through it, I really like using the 2D simplification. It massively speeds up models. Before this was available, you might run a study, a pie slice, instead of running the whole circular model, and you're still looking at a few hours of solve time. When we can run these things with 2D simplification, we're looking at seconds. Even with a really fine, detailed mesh, solve time for this model with a couple of seals in it is still under 1 minute. So we're going to use that to look at a door seal. Very typically, people that are developing seals are building up a compression load deflection curve, essentially a force versus compression relationship. So in this model, I've got a door seal and I built an indenter that's going to press down on it. We're going to use contact, which is actually a nonlinear boundary condition, like we talked about earlier. And I don't like to analyze more than I need to. This is symmetric, so I can just cut a section through it. And I can start a new study, choose nonlinear, and now I check off the use 2D simplification. And it's going to say, okay, is this a really thin section, or is this a really long section? And in this case, it's a really long section. And we pick a plane that we're going to cut that section with. And the front plane should do it. And we get our preview. And we tell it our section depth. And now we can start analyzing this model in 2 dimensions. And it's the same process as we did before. We need to maybe fix one part, and in the other case, we're going to move this indenter a certain amount. So I can just go in. Now I'm working in 2D. I can fix maybe the bottom faces here on the seal. And then I want to tell this indenter to move. So instead of applying a force, I'm going to drive this with a fixture. So I can pick the indenter face or edges and say that, hey, they have to move a certain distance. And my arrows give me feedback. Let's say I'm going to move this 10 millimeters. And then left and right, I don't want it to move at all. And we can have this indent and then come back. So I could define that with a curve to load and unload. So for example, at time at a half a second, we could be fully indented and then remove the indenter at 1 second. That's the fun part about being in nonlinear, because our loads can vary with time. And then I need to define interactions between the bodies. So this far, we haven't had more than one body in the model. Now we have 2, and I need to define their interactions between them. So we can do contact sets. So no penetration means they can't pass through each other. So I can pick this face and this face. And in this model, I'm going to compress it so much that these 2 faces are going to come in contact. So I can do another contact set between these edges if I like. And then my last fixture, because I did cut a slice through this, I want to apply a symmetry condition to the symmetric edges. We can go ahead and mesh. And that's the basic model setup process. So we'll jump over to the symmetrical compression load deflection curve that we've already got set up. And we'll slow up the animation. So we've got the contact between our indenter and the seal, and it's starting on one face, and we're getting it on that second face as we deform. We've got the self-contact inside the seal. And now if I was a seal supplier, the key piece of data, in addition to keeping the stresses within an allowable, stresses and strains within an allowable limit, I'm going to want to know the forces that it takes to drive this inventor. And it's simple enough to extract. We can say list result forces in the model, and I can pick the faces that I'm driving. And say show me the force. And then I want to see that force over the full analysis so that I can determine my CLD curve for this seal. And then it's just simple enough. If we want to make changes, we can just create another configuration in SOLIDWORKS, because I can duplicate my studies and pick different configs. So it's possible to have multiple versions of the seal in the same SOLIDWORKS model and essentially not have to reset up our model. If we blow away a face that had a fixture on it, we might need to reassign that, but other than that, the model is set up. And the interesting part about the hyperelasticity is we talked about, is the stress strain curve the only info I need? For hyperelastic materials, for the most part, we actually need multiple stress strain curves. And you'll see in the checkbox for the hyperelastic material properties, I'm saying use the curve data to come up with my constants. There's a couple constants, or can be 2, 5, or 6 actually, for hyperelastic materials. And those are derived where a simple tension stress strain curve, which is very similar to the tensile test that we use for other materials. And then there's a planar tension and a biaxial tension curve. And these all require different test fixtures to take this data. And there's quite a few test labs out there that will do that. Or as I said, some Google searches, and we can start to find some representative values. So that's a nice example of hyperelasticity along with 2D simplification. We can also plot this out in 3D, and we can tell our boss that we spent all day working on this. And that our computer was eaten up for 4 hours while this was solving, but the reality is this is less than a couple minutes solve time.